My name is Ron Bonica from Juniper Networks, and today we're going to go over the fundamentals of IPv6. I understand that some of you are new to IPv6, some of you are considering deployment, some of you are IPv6 experts. So I'll try to talk to the entire audience. First, what's the motivation for IPv6? When IPv6 was first conceived 27 years ago, the motivation was big address space and a few other things. We're going to take a look at a few aspects of IPv6, and the first is the addressing architecture. Clearly, the motivation was big addresses, so let's take a look at those big addresses. An IPv6 address is a 128-bit identifier for an interface or a set of interfaces. This definition is frequently stretched by encoding other things in the address. For instance, I've seen additional diffserv code points encoded in an address. We've seen segment routing functions and arguments encoded in an address. But the canonical definition is an identifier for an interface or a set of interfaces. Now, a 128-bit address is pretty intimidating. How do we write them down? How do we remember them? Well, the preferred format is in the first bullet point here. X:, 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 where each X is 1 to 4 hexadecimal digits, 8 16-bit pieces of the address. It's even hard to say that. So let's take a look at some examples. ABCD, EF, 01, 2, 3, 4. What you're seeing here is that between each colon, you're seeing something that represents 16 bits. Each letter represents 4. So the letter A represents represents 4 bits, so does the letter B, C, D. Now, it's not necessary to write the leading zeros in each field, but there must be at least one numeral in each field. So let's take a look at this address, the second one here, 201 DB8 008 800 200C, and so on. Well, if you take a look at the zeros, we didn't have to write 0000. Only have to write the most significant bit, the most significant bits, and make sure that there's at least one digit in there. Now, let's say for a moment that you have a long run of zeros. For instance, you have something like 201 DB8 008 800 200C. Well, you can compress those two zeros with 2 colons. So 201 DB8 : 8 800 200C 417A is exactly the same address as the one above it. It makes writing the addresses much, much easier because you'll frequently find long runs of zeros in an IPv6 address. Now, you'll notice as I stumbled trying to pronounce the addresses that, yeah, they're still long, they're still hard to talk about, but using this double colon strategy really does help. There's an alternative form to represent a IPv6 address that's useful when you're embedding IPv4 addresses inside an IPv6 address. If you take a look at the address in the first bullet, X:, 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 D period, D period, D period, D. Well, what you're actually seeing is the high order bits are just plain old IPv6 addressing, where each X represents 16 bits. And the low order bits are plain old IPv4 addressing, where each D represents 8 bits. And that's very convenient in environments where you're using some transition mechanisms to make IPv4 and IPv6 interoperate. As it turns out, there are many ways to represent some IPv6 addresses. The rules that I just gave you really aren't enough to give you a common way to represent everything. For instance, let's say an address has four zeros in it. Two of them are adjacent to each other. Another two are adjacent to each other. Where do you put the colon? Because you can only have one colon. Where do you put the double colon? Because you can only have one double colon in an address. Well, see RFC 5925 for preference recommendations. It's really a good thing if everybody abides by 5925, because then grepping on an IPv6 address becomes a tractable problem. So now that we've talked about these big tongue twisters of addresses, let's talk a little bit about IPv6 address types. We have unicast, anycast, and multicast. A unicast address identifies a single interface. And when a packet is sent to a unicast address, it's delivered to the interface identified by that address. An anycast address identifies a set of interfaces. And when a packet is sent to an anycast address, it's delivered to one of those interfaces, but only one of them. Now, generally, it's delivered to the interface that is closest as defined by a routing protocol. And then there's a multicast address. A multicast address is an address that identifies a set of interfaces. When a packet's sent to a multicast address, it's delivered to all of the interfaces. That's the big difference between anycast and multicast. Anycast is set to one of many addresses. Multicast is sent to many of many addresses. There are no broadcast addresses in IPv6. That functionality has been subsumed by multicast. Now, like IPv4, we have this concept of address scopes in IPv6. A globally unique address is called a global unicast address, a GUA. It's globally unique. There's only one of them around the whole planet or the whole galaxy if you're doing interplanetary stuff. And it's fully routable. A router will route a packet that has a GUA source and a GUA destination. The next is a linked local address. The linked local address is unique to a link. Now, what does that mean? Well, let's say you have a node with 5 interfaces. It's connected to 5 interfaces on their neighbor, and they may all have the same address. Now, does that mean they're all the same interface? Does it mean they're multicast, anycast? No, it doesn't. What it means is the scope of that address is limited to the interface. When you see a link local address, you know that it is unique only to the link. Routers won't forward packets that have link local source or destination addresses. What does that mean? A router can originate a packet with a link local source or destination and send it to a neighbor, but if it receives a packet with a link local source or destination, it will not forward it on to a neighbor because there's just not enough context to know which neighbor there is. And even if there were, how would the neighbor ever get a packet back to the source because the addresses were all linked local? Now, these link locals, you'll see that they're very useful for on-link protocols like Neighbor Discovery. We'll talk about that in a little while. We have a couple more scopes. One is called the unique local unicast address. It's guaranteed to be unique within a domain. It might even be unique globally, but there are no guarantees. And it's used to isolate subnetworks from the global internet. Now, when people see ULA, they tend to say, oh yeah, this is just like an RFC 1918 address. Well, yes, but not exactly, almost. And we'll talk about the differences between ULA and RFC 1918 later. Finally, we have an unspecified address. That address is 00000, all 0. It indicates that the node that is speaking has not yet been assigned an address. It's used in Neighbor Discovery. And of course, a router won't forward a packet that has an unspecified source or destination. For for fairly obvious reasons. One final scope is the loopback address, : 1. You should never see this on the wire. Loopbacks are used for sending, when devices send packets to themselves, they'll use this loopback address. But except in one funny exception case, that being MPLS ping, you won't see a loopback address on the wire. And in MPLS ping, when you see it in the wire, it will be encapsulated in something else. Okay, let's talk about what these addresses look like. Well, a GUA, a global unicast address, a standard one, has a global routing prefix, N bits, a subnet network, M bits, and an interface that is 128 minus N minus M bits. And in this case, N plus M must equal 64, and the interface must also equal 64. But there are exceptions. There's an exception for point-to-point interfaces. You find that in RFC 61 and 64. And when other things are encoded in the low order bits of the IPv6 address, you will also see this rule bent a little bit. We also have IPv4 mapped IPv6 addresses. They start off with 80 bits of zeros, 16 bits of ones, and finally 32 bits of an IPv4 address. ULAs start with FC00, 7 bits, an L bit that talks about how the global ID was generated. And right now, there's only one way to do it, and I think it's with a pseudo-random number generator or something like that. Then there's 40 bits that has this global ID. The global ID identifies the subnetwork. Now, one thing that we might note here is global ID is a bit of a misnomer. If it was generated by some random method, how do you know that it's global? Well, you really don't. You just know that 2 to the 40th is a really big number, and it probably is. And then an interface ID, 64 bits. Link local starts with FE80, 10 bits, 54 zeros, and 64-bit interface ID. Now, you might be seeing a pattern here. Everybody has a 64-bit interface ID. And some protocols you're going to see at the end of the presentation actually rely on that. We'll talk about those when we get there. A couple more special unicast addresses. The loopback, : 1, unspecified, : 0. Let's talk about multicast address formats. They always start out with 8 bits of FF, flags, 4 bits. 3 of them are used. One talks about rendezvous addresses being embedded in the address, how the prefix is assigned, transient. And we won't go into those in any great detail today because multicast is almost beyond the scope of this conversation. I just want you to know that there is a multicast address format. And we have some well-known multicast addresses, all nodes, all routers. Now, let's talk about the addressing model. This may seem obvious, but it's really important. IPv6 addresses of all types are assigned to interfaces, not nodes. That includes the loopback interface. It's assigned to the interface and not the node. All interfaces are required to have at least one link local unicast address. So no matter what an interface is, it's got a link local. A single interface may also have multiple IPv6 addresses of any type: unicast, anycast, multicast, or of any scope. So an interface might have a 3 unicast addresses, one of which is link local, one of which is global, one of which is ULA. It may subscribe to a few multicast groups, so it has a couple multicast addresses, and it might have an anycast address too. Unicast addresses with a scope greater than link local are not needed for interfaces that do not originate or consume packets on their own. So let's say for a minute you have a router, and the router has a loopback address. It consumes packets, so it needs say a GUA address. But all of its interfaces, they can actually get away with having just link locals. There's an exception here for link aggregate group. Sometimes 2 or 3 interfaces behave as one, then they all need their own address. So let's talk a little bit. The amazing thing is the motivation for IPv6 here was to have big addresses. And we spent a good half of this presentation talking about what an address looks like and how it's scoped and what its semantics are. Now let's talk a little bit about the IPv6 protocol itself. Well, a protocol, like any other protocol, provides services. And in IPv6, we can talk about basic services and extended services. The basic ones are next hop identification and forwarding. Get a packet, look at it, decide where to send it. Diff serve and echo. Once you've found the interface you want to send it on, what queue do you want to put it in? Echo, do you want to have any kind of explicit congestion notification? Flow identification, important for equal cost multipath. We'll talk about that later. Loop, well, it's not so much loop prevention, it's a certain amount of looping can go on in either IPv4 or IPv6, but it can't go on forever. So we'll call it loop prevention. And delivery to upper layer protocols. Those are all the basic services. There are also some extended services: traffic steering, fragmentation, authentication, encryption, and extensions that may come in the future. These are all optional. Every packet, IPv6 will deliver basic services to every packet, but extended services only to the ones that have extensions in their header to request them. So let's take a look at these basic services. We said there's a basic IPv6 header. It has a version, it has TOS bits, and the TOS bits are diff serve and echo. It has a flow label that identifies flows, a payload length, the next header, a hop limit, which is what we call the TTL now, a source address, and a destination address. So let's talk a little bit about some of the advantages of this. Actually, let's go back to this slide a bit. You'll find that there are fewer fields in the IPv6 header than there were in the IPv4 header. Well, how can IPv6 be an improvement on IPv4 if it has fewer fields in its header? Well, we'll see in just a second. But before we go there, let's talk about IPv6 and and ECMP load balancing. There's a 3-tuple that provides enough entropy for ECMP load balancing: the source address, the destination address, flow label. These 3 can be found in fixed positions in the IPv6 header. They're in that basic header. So if you're going to do load balancing on those 3, it's really nice to have them in a fixed position at the beginning of the packet. Now, an implementation may also load balance using a 5-tuple that includes the source and destination port. This requires the implementation to parse more of the header chain to get out to see what the source and destination port is. Sometimes this is possible, sometimes it's not, depending on the hardware. But in most cases, it is possible. Now, let's talk about this extension header chain. Let's say for a minute, we have a packet that needs basic IPv6 services. It needs to be forwarded. It needs to have its hop limit constrained. But it needs a few other things. Let's say this one also needs a little traffic steering and a little special treatment at its ultimate destination. Well, what we do in this case is we put IPv6 extension headers between the basic IPv6 header and the upper layer header. In this case, the upper layer is TCP. So we put a routing header right after the IPv6 header. So in IPv6, you look at the next header type, it'll be routing. And if you look at the routing, it has a next header type. It'll be destination. And destination's next header will be the TCP header. So what you do is, let's say you need some service that is an extension service, fragmentation, something like that. Well, then you insert the fragmentation header between the base header and the upper layer. But you only do it when you need fragmentation. You don't carry that weight in the base header for every packet, even though very few packets are fragmented. So let's take a look at some of these extension headers. Two of them are the hop by hop and destination extension headers. The hop by hop extension header comes right after the base IPv6 header. You know, if it's in the header chain, it must be right after the basic header. And the destination options, well, you can have two of them. One before the routing header, if there is a routing header, and the other at the absolute end of the extension header chain, right before the upper layer header. Now, what does this option look like? Well, it has a pointer to the next header. It tells you how long it is, and it has a list of options that it carries. Now, the length is computed kind of strangely. The length is the number of 8-bit chunks in the header, including the next header and the extension header length, minus 1. So if you have an 8-byte hop-by-hop extension header, the header extension length will be 0, which is a little bit counterintuitive, but we've all gotten used to it over the years. And another interesting thing, the maximum length of these two extension headers, the extension header length is 8 bits long. So theoretically, the extension header can be 2K long. Now, the extension header, the hop-by-hop and destination extension headers carry one or more options. And this is what an option looks like. It has an option type, an option length, measured in bytes, and option data. And there are a couple dozen of these. This format, hop-by-hop and destination options header, and the options, you'll see it, it's identical for the two. They are both a bundle of options. If you take a look at the option type, you'll see the first 2 bits, they're called the ACT bits, indicate the required behavior when the processing node doesn't recognize the option. And the required behavior might be 00, skip and process the next option in the option header, discard the packet, discard it and send an ICMP message, or discard it, and if the destination address was not multicast, then send an ICMP message. The third bit, the change bit, indicates whether the option data can change en route to the packet's destination. Normally, there are very few fields in an IP header that can change en route to a destination. Maybe dipserv, maybe ekin, certainly hop count. But here, you're finding options with this change bit set are allowed to have their values changed. Now, this was fairly simple until RFC 8200 was published. When RFC 8200 is an update to the original IPv6 specification. It brought it up to full standard. And you'll find in 8200, while RFC 2460 required all nodes must examine and process the option hop-by-hop options header, now it's expected that nodes along the packet's delivery will only examine and process the hop-by-hop options header if explicitly configured to do so. Now, what does that mean? Well, it means that the ACT bits of a option may be 0, 1, which means if you don't understand this option, please drop the packet. But you don't have to drop the packet if you are not explicitly configured to process hop-by-hop options. So, I guess the meaning of that ACT bit, those ACT bits, is well specified. We understand what it means. It's just a bit convoluted. Let's talk next about the routing extension header. Let's say for a moment you have a packet and you do not want it to travel the routing least cost path from source to destination. You think there are a few nodes that it must visit on the way because you want it taking some traffic engineered path. Well, we have this routing extension header. It comes after the hop by hop, after a destination, if there are destination options to be processed at each hop, but before all the others. It has a next header, a header extension length, which is calculated the same way as all the others. So this can be a very long extension header. A routing type, and there are, maybe 3 or 4 different, maybe 5 different routing types. There used to be an RH0, which was the generic one. I think there's certainly one for segment routing. There are a few others floating around, but it tells you how to interpret the type-specific data. And there's also segments left, the number of segments that still need to be visited along the traffic engineered path. So it's used for traffic steering, and many routing types defined. Segments left indicates the number of segments yet to be visited. And the type-specific data includes a list of addresses to be copied to the basic IPv6 header destination address. So how do we process this thing? A packet reaches the address in its destination address. It starts processing extension headers. It sees this one. If segments left is 0, it just goes past it because you're now at your ultimate destination. But if segments left is greater than 0, you decrement segments left, take something out of the type-specific data, put it in the destination address, and forward. So this is actually a list of waypoints, encoded in some way or other, depending on the routing type. Next, we have a fragment header, and you'll recognize the fields in this. They are the fields that used to be in the base IPv4 header that were required for packet reassembly. Now, we have some bad news about fragmentation. IPv6 makes fragmentation a little more fragile than IPv4. In IPv4, we had a DF bit that told you whether or not downstream nodes could fragment the packet. So if a packet left the source too large to be sent without fragmentation, it might be fragmented downstream if the DF bit was 0. Well, in IPv6, only the source node can fragment the packet. The source node relies on PMTUD to determine whether fragmentation is required. PMTUD tells the source node what the path MTU is. Well, PMTUD is itself a little fragile. It relies on IPv6 packet too big messages, making it from the point where fragmentation is needed to the source. Well, ICMPv6 packets can be lost, they can be filtered. So there is some chance that a source will be forwarding packets into a black hole and not know it until some upper layer complains. So what workarounds have people found in IPv6? Well, an IPv6 link is required to support 1,280 byte MDU. Hosts generally refrain from sending packets larger than that. So fragmentation is rarely required. Now, where did we come up with this magic number, 1280? Well, 1,500 is a common Ethernet limit. From that, they subtracted 220 or whatever kind of encapsulation anybody dreamed up, and assumed that you would never get in a situation where you need fragmentation. Now, inside of a limited domain, you can send larger packets. And in fact, you can even send larger packets on the global internet if you don't mind taking the risk of PMTU black hole. Let's talk about extension header placement for a while. Extension headers are arranged in an order that minimizes the resources required to process. And here's the order that they should appear in a packet. HBH, destination, but only if there is a routing destination before routing, fragment, authentication, ESP, and destination again. HPH is processed by every node along the packet's path. So when you're processing an IPv6 packet, if there is a HPH coming right after it, it's going to be processed. The next thing you will do is look for a destination option. That one is to be processed by every node that's listed in the routing header. Now, destination options and routing are both irrelevant if there's no routing header. Then finally, when you reach the packet's ultimate destination, you reassemble it. That's where you process the fragment header. You authenticate it. That's where you process the authentication header. You decrypt it if you need to. That's the ESP. And any additional options for the ultimate destination. That's the last destination options header. Now, let's talk about IPv6 extensibility for a second. And first, we'll look at the bright side. In theory, IPv6 can be extended to accommodate any future requirement. Just add to existing extension headers. You don't even need to add to more extension headers. You just add more options for the hop by hop or the destination header. And you have a way to get something to either every node along the path, every node in the routing extension header, or the ultimate destination. And because of this, there may never be a next version of the Internet Protocol because IPv6 is extensible. So there may never be an IP15 or whatever's after that. Now, let's talk about IPv6 extensibility's dark side. Most router implementations can't process extension headers on the fast path, especially considering the fact that the destination and hop-by-hop extension headers, as they're defined now, can be 2K long. Who can do that on the fast path? So what they do is punt to the slow path. This becomes a denial of service vulnerability. It's a DOS attack against the slow path. Many operators block packets with extension headers for this reason. You'll see a study of that in RFC 7872. The IETF is currently redefining the hop-by-hop options extension header to overcome this vulnerability. Stay tuned for more. And finally, we're going to talk about ICMPv6. It hasn't changed too terribly from IPv4. There are many holdovers, destination unreachable, packet too big, time exceeded. But there are some new messages to support neighbor discovery, IPv6 mobility, and other stuff. Okay, next we'll talk a little bit about neighbor discovery. This is new in IPv6. And the big takeaway is that neighbor discovery replaces ARP in IPv6. When you wanted to find a mapping between a MAC address and an IP address, in IPv4 you used a protocol called ARP. In IPv6 you're going to do it with neighbor discovery, and it's basically built on 5 new ICMPv6 messages. Let's talk about what those messages are. There's a router solicitation that solicits a router advertisement from whatever router is on link. These are all on link messages. They'll never be forwarded off link. So you send a router solicitation hoping to get a router advertisement back, so you'll know the address and MAC address of local router. The advertisement gives you exactly what you asked for in the router solicitation. It advertises an on-link router, or 2 or 3 or however many there are, and their attributes. There's a neighbor solicitation, and it's a parallel to the router solicitation. It's soliciting a neighbor advertisement message. There's a neighbor advertisement that advertises an on-link neighbor and its attributes. And finally, a redirect message that's pretty much the same as it was in IPv4. So let's talk about this router solicitation message. It has IPv6 fields, the things in the IPv6 header, and ICMP fields, the things that are in the payload. The source address is an IP address assigned to the sending interface, or the unspecified address if no address has been sent yet. So let's say for a minute that a node has just come up. It has no idea what its IP address is because it hasn't talked to DHCP yet. It hasn't talked to anybody yet. Well, actually, there may not even be a DHCP. That's another big difference between IPv6 and IPv4. You have many ways to configure your node. But it just woke up, it just booted, it has no idea what its address is. So it sends one of these router solicitations with the unassigned address as its source. Typically, the destination is all routers, multicast address, a well-known address. And the hop count is 255. Now, there's a reason for this. This is another security thing. You don't want a router solicitation message getting onto your link that originated many hops away. So if the hop count isn't high enough, you will drop the message. Then the ICMP fields, there's a type, 133, a source link layer address, and that's the link layer address of the sender if known, and generally it is known. And that's your router solicitation message. It gets back a router advertisement message. And the router advertisement message, like the router solicitation, has IPv6 fields and ICMPv6 fields. The source address is the link local address assigned to the interface from which the message is sent. So the router has a link local, it sends the message and says, this is my source. The destination address is the source address of the invoking router solicitation or the all nodes multicast address. So if the router solicitation had a real address on it, a real link local, you send it just to the station that's asking. If it didn't know its own address yet, you blast it out to the whole link. And again, hop count is 255 for security reasons. And the router advertisement message has a lot of payload in it. It has a type, a current hop limit, which is the default value that should be placed in the hop count field, IP header for outgoing packets, an M bit and an O bit that tell you whether additional information is available from DHCP v6 or if DHCP is running at all. These are a bit difficult to interpret. Different implementations interpret them differently, and I won't go down that rabbit hole right now because it's kind of a long story. A router lifetime, and that's the lifetime associated with a default router. 0 if this router doesn't claim to be the default router. So if you're the default router, you say how long you want to be the default router. If not, you just say 0. A reachability time, a retransmit timer. Here's the important part, the source link layer address, and that's the link layer address of the interface from which the router advertisement was sent. So now the recipient of this message can send a message to this router, a point-to-point message or a unicast message, an MTU, and that's the MTU of the link that the router is speaking on, and prefix information that we'll see later used for SLAAC, for stateless auto address configuration. I probably should have mentioned that there are 2 ways to get addresses to IPv6 nodes, DHCP-v6, which feels a lot like DHCP-v4, and SLAAC. There are neighbor solicitation messages, and here I won't read the slide to you, but you'll see that there's a parallel between neighbor solicitation and router solicitation, and neighbor advertisement message. And here the IPv6 fields are actually important. The source address is the address of the interface from which the advertisement is sent. That's a link local address. The destination address for solicited advertisements is either the invoking neighbor's address, the one that he sent in the neighbor solicitation, or the all nodes multicast address. Again, a boatload of payload that tells you about the neighbor, a router flag that tells you whether the neighbor is a router, a solicited flag that tells you whether the advertisement was sent in response to a neighbor solicitation, a target address, and for solicited advertisements, the target address field in the neighbor solicitation message. It's the target address in the neighbor solicitation message that prompted the advertisement. For unsolicited, it's the address of the link, the address whose link layer address has changed. Basically, a neighbor advertisement you would send in 2 cases. If it was solicited or if you were renumbering and you changed your own address. And finally, the redirect message, and that is the one that hasn't changed very much. You can now see how this might work. A router comes up on a link. It might send out gratuitous RAs, it might not. A node comes up. It sends a router solicitation, gets a router advertisement. So now it knows the MAC address of the router. It can talk to it. It knows which of the responders is the default router and for how long. And it also knows some things about prefixes it can use. Now it wants to give itself an address. And let's talk about the SLAAC process. Well, a node can be configured by a SLAAC or DHCP, or both. Let's assume for a moment it's just SLAAC for the moment. What's the concept of operation here? Well, a node forms a linked local address by appending an interface to the well-known link local prefix FE800::/64. So it knows that all link local addresses start with FE800. It then picks 64 digits, 64 bits at random, and forms an address. And it says, I would like to be this address. Now, the odds are very strong that there is not another node on link with the same address, because 2 to the 64th is a really big number. Then it performs something called duplicate address detection procedure. It sends an NS message with the target equal to the link local address that it just picked. So what it's doing is saying, is there anybody else on this LAN segment who's got the address that I've just picked? If there's no response, that's good news. That means that there is no other node with this address. It can use it. Then the node sends, if the node receives an RS message, then there's an issue. He's picked another address, and you need to go in manually, configure it with a link local. But the odds of that happening are very, very slim. The node forms a GUA by appending an interface identifier to the prefix that it received in the RA message, called the GUA address it received in the RA message. And then it does the exact same thing, find out if there's another node on link that is also using that address. If not, it's good to go when it has an address. Well, thank you very much, and I'm looking forward to your questions.
Yay, Ron. Thank you. We don't have anything Nope, we don't have anything online yet. Does anybody want to come up to the mics? Going once. Ron is joining us by telephone from Sterling, Virginia, I think. So does anybody have anything? Bueller? Everybody understands V6 that well? Great. Who'd like to volunteer to teach the second half of this? Is that somebody walking up to the mic in the back? No. Ron, do you have any parting comments since there's nobody at the mics and nobody online?
If you do have any questions, feel free to email me, rbonica@juniper.net.
Ron, where I am, I'm having trouble hearing you with the background echo, so.
I'm sorry, if you do have any questions, feel free to email me at rbonica@juniper.net.
Yeah. Please mail Ron, rbonica@juniper.net. Anybody? Somebody coming to the mic now? No, that's somebody leaving. Okay, Ron, thank you for the presentation. As always, wonderfully done. Looking forward to seeing you as soon as I can in person. And on that note, I think I'm going to say thank you. That closes the morning session.